Okay, guys, so we're talking about working energy and rotation. I don't know that we'll get done because there are some things that I want to go over. When we talk about energy, what determines the total energy of a moving object? The thing that I got to tell you about is, and talk about is, I've got a board set up over here for you guys to kind of look at, is what we need to know, and you guys already know this, but you don't necessarily, is if I take two things that have the same radius, like these two, or if I take two things that have the same thing smaller, who wins the race? If I drop them, if I start them at the top and they roll to the bottom, which one hits the bottom first?
Oh, full one.
This one or this one? Everybody always says this one.
I'd say it would be the same.
All right.
Remember you told me
So,
it should be the same.
here we go. They're starting at the top the same. It's not the same necessarily.
It's the other one. It's the one with the empty.
Now, more dramatically, it's easier to see with the bigger ones. So let's do these two. Which one do you think this one's going to win again?
No, I think the plastic.
Oops.
Plastic here.
You think this one's going to win?
Yeah,
It's metal, actually. It's
Metal.
they're the same mass, believe it or not, they're the same mass, they're just different.
Oh, what? No.
Now,
Oh, the mass is more spread on the outside.
Now, this one lost. Why?
Because the mass is more spread towards the outside wall.
Okay, what do you call that
We had a problem.
between these two?
Like another rotational
Inertia, rotational inertia. Guys, there are two types of energy that are happening when something is rolling down a hill or rolling across the floor. There is translational energy, that is the energy of sliding, and then there is rotational energy. That rotational energy, the more rotational energy, it's a finite amount of energy. The more energy it takes up to make it turn, the less it has to roll, to actually slide. So this one has more inertia because it's got more of its mass towards the outside. Therefore, it uses more rolling and so has less to actually translate. So the more inertia something has, the less translational it has if conservation of energy is happening. Now,
Cars, we need the rubber in the outside to have things, but no, cars don't, just big old thing.
now what about these two?
Are they the same mass?
No, this one actually has more mass than this one.
I just think the smaller one because it has a less radius, so that means less rotation.
But it might be the,
Well, if I could roll them, hang on, here you go. Let's see if I can actually get it to roll this time. Let's see.
The smaller one.
Exactly the same.
Okay.
If they have the same rotational inertia, the mass doesn't matter. It all comes down to rotational inertia. Where is it distributed? So, we'll talk about this. So let's look at it. Keep that in mind though, and we'll look at the mathematics of why the mass doesn't matter if that's the case. So what determines the total energy of a moving object? Both its inertia and total energy. There are two types of total energy. There is rotational energy and there is translational energy, okay? So a rotating object has kinetic energy, and the total kinetic energy is the sum of the kinetic energy of all of the different particles, okay? So now, what type of rotational energy are we talking about? Kinetic energy for rotation. Now, if we did kinetic energy for translation, K sub T, we get 1/2 mv squared, don't we? There's a directly analogous to rotational. 1/2, instead of mass, what do we find? Inertia. And instead of V,
Alpha.
that would be,
Alpha.
alpha is angular acceleration.
Oh, omega.
Omega. 1/2 I omega squared. So if you know 1/2 mv squared and you know how they relate to the other, then you have it. Can I help you? Oh, okay. He's gotta leave at 3, so I gotta go through of this as I can. So, all right. This is the big thing right here. Now, what we need to find out is, and what we're gonna figure out with energy and work, is that now we don't just consider K when we do total mechanical energy. You know, mechanical energy in equals mechanical energy final, initial and final. We don't just have K anymore. We have K translational plus K rotational plus U plus work non-conservative if there is equals K translational plus K rotational plus what? U here, correct? Initial equals final. This is the big change that we're finding. So now it's not just 1/2 mv squared plus mgh, and of course U could be gravitational or spring, right? Usually if we're talking about rolling things, it's gravitational. That we now have this whole extra little chunk, the rotational component of it. All right, a block of mass m attached to a string that goes over a cylindrical pulley of mass m and radius r. If they tell you the pulley has a mass and a radius, that means it also has inertia and is now taking energy out of the system or taking some energy in some way. When the block is released, the pulley begins to turn as the block falls. Calculate the acceleration of the block, okay? So we've got both linear motion and rotational motion. So we've got both F equals ma and T equals I alpha. We saw this last lesson, didn't we? We talked about torques, both used for the mass and the pulley, okay? Direction of motion will be taken as positive direction for both. So what is the direction of motion? Clockwise and down. It's typical convention that we've been using, okay? Normally clockwise would be considered negative torque, but we said just make it the convention as long as you stick to your convention. So if we're looking at clockwise direction, we're talking about the sum of torques is IA, correct? Well, what is the torque here? What's causing the torque on the pulley, guys?
Did you say IA or
I alpha.
The block.
The block. The block is falling, isn't it?
Yes. It's
Okay, so what is the force on the block?
Gravity.
Yep, tension.
Oh.
It is tension this way, isn't it? That's the thing that is directly touching the pulley and causing it to go. We don't include gravity.
Yeah.
Just the tension times what?
Radius.
The radius. Yep. So what we know is that TR equals I alpha. Okay, so what is for cylindrical pulley? We know I. Usually if it's something other than 1/2 mr squared or mr squared for a particle, they'll give it to you directly. You're not required to memorize all those things. Or they'll ask you to, well, I don't know, derive it. Okay, so we have TR. For cylinder, it's 1/2 mr squared, isn't it? And alpha, we want to know what? Acceleration, so alpha is A over R, is it not? So, marking some stuff out that we know that this R and that R squared go away, don't they? Remember, you cross multiply it and it's R squared on the other, both sides? Yeah, that one. So T equals 1/2 MA squared. Okay? We don't know what the tension is, so now we've got to actually go into Newton. What?
Would it just be 1/2 MA or this?
Oh, did I do A squared?
Yeah.
I'm sorry. Yes, thank you for catching that. Yeah, MA. All right, so now we need to know what the tension is, so we go into Newton. Free body diagram.
The tension equals the mass of the
Tension this way, and what's this way now?
Is that not M?
Little mg, right? Because big M, this is big M, that's little m. So what do we know? Sum of the forces, which is little ma, is equal to what?
Tension minus the
Mg minus T, not the other way around.
Oh.
Downward.
Yeah.
All right? So now we have to solve for tension, correct? So tension is equal to little mg minus little ma. And now we take all of this and we plug it in there, don't we? So we have 1/2 big MA equals mg minus little ma. Bring everything with an acceleration over to the other side. Pull A out and divide. Correct? Now, what would happen if the block and the pulley were both the same mass?
Would it not be A squared?
No.
No, you're factoring out A. What would happen if the block and the pulley are the same mass?
It would just be one single. Right? It would just be one singular instead of using cycle.
Yeah, it'd be 2/3 gravity, wouldn't it? Yeah. Yes, no? Yeah, look, if m equals m, this is just an aside, you get the acceleration is m over g and then 1/2 m plus m, isn't it?
Yeah.
So this becomes 3/2 m over m. M's go away, 3/2 flips over and becomes 2/3 g.
Oh.
So if the mass and the pulley are the same mass, then
Just be 2/3.
2/3 of gravity. Which I wanted to show you because that just really shows you that it's going to fall slower when this is turning, because this is taking some of the energy, isn't it? The turning of the pulley is actually reducing how fast that mass falls. All right. Work energy theorem. What is work? FD. What? FD theta?
Yes.
Right? If we're talking about a rotating body, D, and really D should be what? R. So FR theta. Well, what is FR? Torque. So it is torque times theta. The change in the rotational angle. And remember, work is also the change in kinetic energy. So the change in kinetic energy is torque applied over some angle. That's really what this means, isn't it? Brain goes faster than hand does sometimes. Applied over some angular displacement, right? And it's only the component of the force perpendicular to the axis of rotation, right? Because that's the only one that gives you the rotating torque. All right, so what is power?
Work over time.
Power is dW dt, right? Now, total kinetic energy. Remember what we said. Total kinetic energy is going to be what? K rotational plus K translational. So it becomes 1/2 I omega squared plus 1/2 mv squared. Okay? So look at example B. What does it say? It says the wheel on the ground keeps on turning. Show that the radius of the wheel does not affect its total kinetic energy. So what is the kinetic energy? K equals 1/2 mv squared plus 1/2 I omega squared, correct? Okay. For a wheel, for a cylinder, we could call the wheel a cylinder. We could call it 1/2 m, what? 1/2 mr squared. So this becomes 1/2 mv squared plus 1/2, and this is 1/2 mr squared, and v squared. What is v? Or what is omega? Excuse me. Omega is v over, yeah, alpha is a over r, omega is v over r. So this becomes v over r quantity squared. So it becomes v squared over r squared. And what happens to the r? So we have 1/2 mv squared plus 1/4 mv squared, which ends up being what? Three-quarters mv squared. It actually increases the kinetic energy, doesn't it? In that regard. Now, here's the big thing. This assumes that the wheel rolls without slipping. If the wheel starts to slip, all bets are off. You lose energy, you don't get the rotation, do you? If the wheel is slipping, you don't get the rotation. So now, why does this thing end up equaling what it equals? I need you to pay attention to what this means. If we have a wheel, and I don't like these pictures as well. If we have a real wheel that is rotating, the big thing that I need you to look at is this. For a rotating wheel, we know that it has a force going this way and a force going that way. If it didn't have both of those forces, it would not what? Rotate. It would not rotate, would it? Now, depending on where it's going, you see them all changing directions, don't you? Those are the big ones. If it is sliding without rotating, it is simply going, both of them in the same direction. So rolling without slipping becomes, this guy gets bigger. Think about why. That's this plus this, because rolling without slipping is a combination of those two, is it not? In other words, you're taking this guy plus this guy to equal this guy. So now what happens to, look at this versus this. What happens to those at the bottom touching the ground?
Oh, they all cancel out.
They cancel out,
Oh, I just.
which is why it doesn't slip. The translation doesn't just slide this way. If it's the right combination to roll without slipping, what would have been slipping this way cancels out the rotating going touching the ground this way.
Okay.
Which means that that guy at the top here, this guy plus this guy gives you this, and this torque acts as a torque which continues to cause it to what?
Oh, okay.
So then you still get these two canceling. It's on the verge of slipping, it's not going to slip, right? These cancel, this is big, continues to go. Notice how it stages down, doesn't it?
What would an example be rolling without slipping?
Rolling without slipping?
Fire.
Anything, a tire. This rolls without slipping, if it's got enough friction. Rolling with slipping, at some point for it to rotate, it has to become without slipping, doesn't it?
Okay.
Here's rolling without, if I shove this fast enough, it slides first, and then
And then you wrote, oh,
friction
okay.
kicks in with the contact here. And remember, with the tire, you get that contact, doesn't it? Yeah, and you get the contact with this between this and this,
Okay.
okay? Which cancels out the sliding this one. And then you get that build up the extra force here, which then causes it to continue to rotate forward. Anyway, so weird thing, which is why I wanted to make sure you had the picture of it. So,
So it slides so far forward that the forces on the top completely outweigh the forces on
Tip.
the bottom. And
continue to
goes
tip
the
it,
top.
tip it, tip it, tip it, tip it. Yeah, kind of think of it that way.
Okay.
So when it's rotating, each point on the wheel has a different linear velocity. Okay? When it's sliding, each point has what?
The same.
Yeah, it's the same linear velocity. Rolling without slipping, the point of contact that would be right here, wouldn't it? The point of contact between the wheel and the surface. Has zero velocity. And that would be linear velocity. It has rotational velocity, doesn't it? Has zero linear velocity, causing it to tip. Okay? Friction is what's used to convert rotational kinetic energy to linear kinetic energy. Make sense? Looking at this picture?
It does now.
Yup. The magnitude, and if you read this, it makes so much sense. The magnitude of the negative rotational work done by friction equals the positive linear work done by friction. That right there is a huge thing. Thus, friction does what? By no network on the wheel. There's no network done on the wheel. Positive and negative cancel each other out. All right, let me answer this. See if I can answer Jesse's question real quick, and then we can get him on his way, and I can help you guys with it. Okay, that's one of those where you're going to have to square probably both, because then we don't put really 60 to 15 is basically squared, 15 squared. And when we want the other side, you have to do one to the other side. You're going to have to like do secant x equals 1 minus 15 minutes. Now for both sides. So secant squared x equals 1 minus 2. So secant 15 minutes equals or
Did
was.
you look at the printer printing in this integration class?
Okay.
The printing?
Or-
I was working on the other one.
Two.
Are you in that?
Plus.
I don't understand the two linear.
And then
I get the rest, but I go into I'm doing it.
Yeah.
Two linear.
Just secant squared right
Why
here.
did you have
Secant
some
plus 1
completely
equals negative 15 squared plus 1, and you got all those.
That's where we cut off.
Yeah, I think I recorded the rest of those notes. It's
Yeah,
on
but I
here.
didn't understand like how we got to you from you.
I also brought
Square
a
those
thing to weld.
Okay, I got it.
All right, cool. All right, guys. So now let's look at, here we go. Example C. Solid wheel of mass M and radius big M and radius R moves up an incline as shown. So it is rolling up the incline. The speed of the ring is V as it enters the incline. So it has initial velocity V. Gives you a little background here. When friction is present, used to convert rotational kinetic energy into linear kinetic energy. We know that. The magnitude of the negative rotational work done by friction equals the positive linear work. No net work done. We got that. It's just a repeat of what they said. How high up the incline the wheel goes if the wheel slips while going up the incline. What does that mean? That means the incline is what? Frictionless. So if the incline slips, is there any rotation? That's what you've got to ask yourself. No, it may have been rotating up to that point, but the minute it hits the incline, it's just sliding, isn't it? So this is your traditional mechanical energy in equals mechanical energy out. In other words, U initial plus K initial, U final plus K final, right? So if at the bottom of the incline, is there any gravitational potential energy? No. So this goes to 0. At the final, does anything zero out? Kinetic energy, because it wants to know how high up it goes, so it's going to be at a stop. 0. So basically what we have is the traditional 1/2 mv squared equals what? mgh. M goes away. So h is equal to v squared over 2g, right? Then it says, find out how high it goes if there is no slipping. In other words, friction is present. What does that, how is that going to change my problem? You're still conserving energy, aren't you? Do we have to count the friction? No, because it's canceled out, right? That's what that whole statement up there says, is we don't have to consider friction, work non-conservative. It's done a purpose, it's caused the rotational. So so we have U initial plus K initial equals U final plus K final. But do we have U initial? Starting at the bottom. Comes to a stop, so K final is still 0. But K initial
Is higher.
is now a combination of,
Wait.
no, it really is. It's a combination of rotational plus translational equals mgh, doesn't it? So now we've got 1/2 I omega squared plus 1/2 mv squared equals mgh. M doesn't go away anymore, does it? At least not yet. This is a solid wheel. So its inertia is 1/2 mr squared, isn't it? So this is 1/2 mr squared. This becomes v squared over r squared, doesn't it? It's 1/2 mv squared equals mgh. M does still go away.
Now that we have the,
Yep, we got r squared's going away, so we have 1/4 v squared plus 1/2 v squared is 3/4 v squared equals gh. So h is,
3b squared over 4g.
yep, 3v squared over 4g versus v squared over 2g. Okay. How would the answer to B change if the wheel were, well, it says if the wheel were solid. What I'm going to say is, what would happen if the wheel weren't solid? What would happen to the energy? How would the answer to B change if the wheel were,
I was wondering if it was just a typo.
what? Hollow? With the same mass. What's the only thing that's going to change here? Yeah. I for the hollow is going to be what? What is inertia for a cylinder? cylindrical hoop, it's mr squared, isn't it? So I becomes mr squared instead of 1/2 mr squared. So we get 1/2 mr squared v squared over r squared, right? Plus 1/2 mv squared equals mgh. M and m go away, r squared and r squared go away. So instead of having 3/4 v squared over g, we have h equaling just v squared over g. Think about why that is. It has what? More inertia means more initial rotational energy. Doesn't it?
It takes more to rotate.
Yeah. Therefore, wheel goes higher. Okay? So the wheel ends up going higher.
Wait. Oh.
It's already rolling when it hits the bottom, right?
Okay. Yeah. So now it takes.
It didn't say it would take the same amount of time
Because it takes.
to get there. It just says it'll go higher.
Because it takes more to stop it, really.
Yeah.
Okay. Yeah. It makes me think.
Yup. Now you're getting your head wrapped around. All right. Example D, rolling down an incline, a wheel of radius M, a mass M and radius R, typo. Yeah, I know. Without slipping down an incline, find the linear speed of the center of mass of the wheel when it reaches the bottom of the incline. So, best thing to do, since we know it's going down a height h, is conservation of energy, right? So, conservation of energy says U initial plus what? K initial equals U final plus K final. We know in the beginning it doesn't have any kinetic energy because it starts from rest. And at the bottom it doesn't have any gravitational potential. So at the top we are at mgh. At the bottom we are what? Rolls without slipping, so 1/2 I omega squared plus 1/2 mv squared. It is a solid wheel, correct? So if it is a solid wheel, I is equal to 1/2 mr squared, correct? So mgh equals 1/2 mr squared, v squared over r squared for omega, plus 1/2 mv squared. I know. M goes away, r squared goes away. We got 1/4 plus 1/2, so we've got what? Linear speed. So we've got GH equals what? 3/4 v squared. So v is going to equal the square root of 4/3 GH. Yep. Now, calculate the acceleration of the wheel down the incline. You see acceleration and you should think torque if it's rolling. So this is a torque problem. What's causing the torque?
The rotational angle.
The force of friction.
Oh.
It is a positive torque, since it causes the wheel to rotate. But a negative force, isn't it? But it is a positive torque. So let's look at what we got here. We've got this thing come in, what? Was it going uphill? Downhill. So this thing is rotating, it's rolling downhill. It's going that way. We want to know its acceleration down the hill. However, the only forces we have that act on it that we care about at this point is what? We got mg coming down from the middle. You need to know where to put these forces, don't you? Matter of fact, I'm going to get rid of this one right here because I know nothing's actually coming out of that. Now, we have friction. Friction is a contact force. This is the force of friction. And then what do we have? What's the other force here? Normal force. Okay? Notice that I did not place those all at the center of thought, did I? Guys, this is a biggie. If they give you a circle like this and ask you to draw a free body diagram for it, they're looking for you to put gravity from the center of mass, normal force from the point of contact with the plane, and friction, because it is a torquing force at the point of contact between the plane and the rolling object. Okay? It's important, yes. So now, let's talk about sum of forces. Sum of forces this time are going to be equal to MA, right? So we have the force of friction. We know this thing's going that way, so now we need this guy, don't we? Correct? This is theta, right? Up there in that corner, we've got theta. So we know this is mg sine theta, correct? So we know MA is mg sine theta minus the force of friction. So MA is equal to mg sine theta minus what? We could do the mu times the normal force and all that, but I don't really want to because I can now treat it as torque, can't I? Sum of the torques is equal to I alpha, is it not? Well, what is the sum of the torques here, guys? Force of friction times the radius of the thing, isn't it? I is 1/2 mr squared, and this is A over R, isn't it?
So it's mg sine 1/2 mr squared.
Got the R's going away,
Oh,
right? So the force of friction is really 1/2 MA. Now, where that came from, just for everybody at home who's wondering, this was force of friction equals 1/2 MA, right? So then what I did was said, okay, I took this and put it in for this to become that. All right? So now, let's take this, add this to the other side. We end up with what? 3/2 MA equals mg sine theta. Look what happens to M. So what is A?
2/3 sine theta.
We knew it was going to be less, right? Because of the rotation, the acceleration goes down. All right, so to prevent slipping, what are the conditions to prevent slipping? Do you have any idea?
Friction.
Force of friction has to be equal to this to prevent sliding, okay? So the force of friction has to be equal to that 1/2 MA.
Could it be more?
Could be more. but that's the tipping point, right? Two conditions are this. The velocity has got to be equal to r omega, and mu has got to be equal to mg cosine theta. Look, the force of friction we know is mu times the normal force, isn't it? So mu, this is going to be mg cosine theta, isn't it? And this is equal to 1/2
Austin High School.
MA.
We got a great day, and it's a beautiful, beautiful day outside.
Well, what's A?
Tonight, we got a couple of announcements. I'd like to say congratulations to our baseball team as they won 2 games on yesterday. Also, congratulations to our soccer team as they swept Hartsville yesterday. Great job, boys soccer. And also, big victory by our Austin All-Stars today over James Clemens. Also, students who were able to go to the game, thank
Oops,
you for
I
cheering
forgot
for all
M
the
here.
students. Thank
M.
you. Y'all made me
Forgot
proud
the M there.
again. We got a couple
Now
of
look.
announcements as far as sports. Our boys soccer
M goes
playing
away
at
again,
Taylor
doesn't
High
it?
School on tonight. Our softball is at Gardendale, and our JV girls soccer will be at home against
Mu is equal to
and our tennis will be at home as well.
2 and 2 go
Again, we
away,
had a
so
great
1/3.
day because of those victories. After I finish announcements, all students will be released.
G goes away.
After I finish announcements, all students will be released. Students, please drive slow on Motors Road and Shade Road.
Sine theta divided by cosine theta, right?
We'll see
So
everybody
1/3.
tomorrow. Have a good day.
Do you remember when we talked about static friction? We said the coefficient of static friction was tan theta. Well, if it's a rolling object and all we're trying to do is keep it from rolling and not sliding, or sliding and allow it to roll, it's only 1/3 of the static friction needed. So it doesn't require as much to continue to allow it to tip over and continue to roll. If it gets to be too high, then what happens? It just still rolls. Yeah, but it's gonna, yeah. All right, guys. We've got one last thing to go next time. I think that we'll stop here. We'll pick up. Next time we're going to be talking about, we're going to finish this up and talk about angular momentum. All right? So we got a lot to do in angular momentum. You need to do as much of the 5-4 exercises. Don't worry about 5-5. We didn't even get there. 5-4 exercises as you can. Some of them maybe we haven't finished this last one, this last